It's great. Welcome everyone to another CAN seminar series. We have a distinguished speaker with us today, and actually it's my utmost pleasure to welcome Randy Weingart, who is a great friend for over 20 years. We worked together quite a bit in related to aggregate industry and ICAR, the Center for Aggregates Research. And Randy has been a technical director and actually an aggregate person with Capstone Corporation until 2016. He has been the director of materials there for about 27 years. That is with a mining engineering degree from Colorado School of Mines from the 1970s. So, but in his role in Capstone as director of materials, he was very much involved all the time with research, and that's how I got to meet with him early in my career. That is as assistant professor back in the late 90s here. And over the years, we have been doing a lot of good work in various different committee work related to ICAR, Center for Aggregates Research, as well as of course, TRB, Transportation Research Board, the Aggregates Committee has been a member of. I recruited him on that committee as well. Did. And, but over the years, we worked on many other, again, task force meeting groups and other places. Especially happened to visit them several times on these construction sites and quarry visits too. He's a great guy to go around and tour a quarry together with. He will tell you all about it, actually, and you will learn a lot. So anyway,
thank you.
With that, in his current position for 2 years as the technical director with the National Stone, Sand and Aggregate Association, I think Randy is really doing a great job for all of us from the technical point of view with the know-how and with the expertise and experience. And for that, I would like to really thank Randy one more time, because he's really an asset to the industry, to the aggregate industry, and to, in general, pavement community. So with that, I would like to welcome you, Randy, and we look forward to hearing your talk.
Good. Thank you. Well, I must say I do really appreciate, especially the thanks to your students, the faculty, and certainly the staff here. It's been pretty impressive for me. I hope you're as impressed with my presentation as I have been with what you've done for me since I've been here. So I really have enjoyed seeing the campus and the facilities that you have here and understanding it. I think it's a great place to be and a wonderful place to learn, especially with people like Marshall Thompson and Errol Tuitmuller. So thank you all for having me. And I'm going to start this presentation with kind of wisdom from above. This is an adage that I think I like to follow. It makes good sense. So a man was flying in a hot air balloon, okay? And he realizes that he's lost. He reduces his height, and spots a man down below. So he lowers the balloon further and further and shouts to the man on the ground, "Excuse me, can you tell me where I am?" And the man below him says, "Yes, you're in a hot air balloon hovering 30 feet above the field." And the balloonist says, "Well, you must be an engineer." And the man replies, "I am." He says, "How'd you know?" "Well," says the balloonist, "everything you've told me is technically correct, but it's still of no use to anyone." And the man below says, "Well, you must be in management." And the man below says, "Well, you must be a man." And the ballooner says, "I am," replies the balloon guy. "But how did you know?" "And well," says the man on the ground, "you don't know where you are or where you're going, but you expect me to help. So you're in the same position you were before we met, but now it's my fault." So today, even though I might be that engineer on the ground, I'm trying to play a role of the pragmatic investigator and apply some of the principles of discovery that I've enjoyed in my career, learning about things that I didn't know anything about. And trust me, I've discovered throughout the career, one of the areas of wisdom is that you begin to realize very shortly that there's a lot more to ever know than you're ever going to understand. So So even though the precise science that you guys deal with every day may elude me because I'm just one of those humble mining engineers, I hope this information will stimulate you and to create in that creativity that I believe is really fundamental to the human species, that we're creative beings and designed for that purpose. So I appreciate all your staff. And so with enough science to be dangerous and even less management knowledge, let's get this balloon off the ground and see what we're going to talk about today. And if I can punch all the right buttons in the right way. You all probably are familiar with this. I'm not going to spend a lot of time, but this is kind of what started it all back in the day, which really isn't that far from this location. Some of the issues at the time is they used crushed limestone as a base material, just as a refresher for those who. It was all well graded, and most of it was about 12.5% passing to 200, which is a little bit high, especially if you have a lot of frost issues. All the compaction was to T99, which is not the highest levels of compaction you might achieve. They compared the cement and bituminous treated gravels. Both were plant mixed in this empirical test study. And it resulted in determination of the structural coefficients for design of unbound aggregate layers of 0.14. And we've been doing that for many, many years. Many of the design protocols in many of the states still use the structural number methodology, even though we've advanced beyond that at that point. And also, I'm sure that everybody here is aware of what an equivalent single axle load is. And so this is just a revisit. This talk was originally given to a bunch of aggregate guys who needed to understand what this was all about. So hopefully it won't be too boring. So the flexible pavements are really about successive stiffer layers from the subgrade to the surface. Each lower absorbs the load as it's distributed to the subgrade. And traditional design in Unbound puts the unbound aggregate at the bottom because it's perceived to be the weakest. Also, something you might want to consider that when we put the unbound aggregate layer on top of the subgrade is the weakest spot. So we try to compact that. Sometimes you're not going to achieve even what you did, you're not going to achieve the proctors that you got in the lab. And so many states, at least in the state of Virginia, require, you had to do field testing and a control strip to see what you could actually achieve in the field based on the subgrade that was there. So we may not actually have as strong or as dense a base as we'd like to have because we're placing it on top of the subgrade. Of course, then we have rigid pavements, concrete. This is a section on 288 in Virginia. And also, in order to accomplish this and do these designs, you have to characterize the materials to begin with. And I'm sure many of you probably run this test, finding the resilient modulus for materials. But we also know that this, I'm going to go out on a limb here, but this may not be the best number to use or information to really build a pavement structure around when you look at unbound aggregate base. And thus some of the issues that we have potentially with MEPDG that's out there now and the research that's being done on it. Uh-oh. And of course the relationship that you have to the CBR and the resilient modulus, the relationship that you achieve. And I think this has probably been modified with time too, but I know that sometimes you can do a CBR and then relate that back to the modulus. So one of the things that's unique about the unbound aggregate base is the stress dependency, so that the more you stress it, the stronger it becomes. And sometimes I think the general construction world doesn't understand that. When we built the inverted section at Bull Run, the contractor that I was trying to get that over 105% of proctor for T180 said, "You can't do that. I can't do that." And I go, "Yeah, you'll be able to do that." He goes, "No, I'm not going to be able to do that." Because he never had been able to do that. Because he's always been compacting the aggregate base on top of the subgrade. But when you start compacting, this is the key for me. If you don't walk away with anything else today, the key is that you're compacting this unbound layer that gets stronger as you stress it on top of a rigid platform. And when you compact it against that rigid platform of cement-treated aggregate base, you can achieve a significantly higher densities and strength than you would normally get. And that's why this system works. When I first went to work, the asphalt industry got me aside and said, "Randy, we don't ever hear you talk about sandwich pavements." I go, "Okay, what are those?" He goes, "Well, you put an aggregate base in the middle. They don't work. We have all the testing. Here's all the reports that says it doesn't work." I go, "Okay." So then I bounced along for 15 years believing that. Well, then I started looking at, well, I'm not sure that there's something to this. You know, this makes sense, and there are countries, South Africa, that are using this, highly successful. It's their primary pavement design. We'll review that a little bit. So, the unbound base and pavements, it's a unique material. It becomes stronger as you stress it more. It's flexible, and it can be optimized. You know, it's best captured when placed near the surface, okay, rather than down deep in the structure, because that's where the stresses are going to occur. And with inverted pavements, the stress state can be 3 to 5 times more than what you would normally find in conventional flexible pavements. So you want to place the base where its optimal location is. And then you can use a thinner HMA layer over the surface. Okay? I think from a design engineer's point of view that we've so long been in the design community where we just naturally talk about flexible pavements, thick layers of asphalt, or we talk about rigid concrete pavements. But we've never really been educated that significantly on what is this inverted pavement and how does it work and can it work. So I think many engineers up to this point who are pavement design engineers have been indoctrinated into two systems and don't really think open about other opportunities. And maybe there'll be new concepts come along in the future as well. But for right now, we want to talk about inverted. Density is critical. Density is really the same as stiffness, but you have to achieve the density in order to get the stiffness, because that's really what you're looking for. So, I have the fat finger. South Africa specifies 86% of apparent specific gravity. So basically what that means is if you take a specific gravity of a material that's 3, okay? 3 times 62.4 pounds per cubic foot water. So you're talking about 180 some pounds per cubic foot of a solid mass of stone. And the South Africans are trying to achieve 86% of that, which would be about 105% of a T180 Proctor, okay? Now, you go to any contractor here in the United States and say you wanted him to achieve 105% of T180 Proctor, and he's going to go tell you, you need to go talk to somebody else because we can't do that. So in many respects, it's just a general unawareness of what the capacity or potential of this inverted pavement design concept could be. So, 86%, that can vary a little bit based on the mineralogy that you have present, whether it's a limestone, whether you have a lot of quartz in it, or you have other heavy metal minerals. So the unbound aggregate base is made easier in compacting it on top of a cement treated base, right? We got that. That's the key walkaway. So we've seen this, so as the CBR improves, we see that we can move up the density, which gives us stronger values on this curve. So this is what we're really talking about when we talk about an inverted pavement. Thin HMA, 6 to 8 inches of unbound aggregate base, compacted on top of a cement treated base, around 4% or less, depending upon what strengths you're looking for, over a subgrade. So let's look at some of the key points just to review. So, you have a relatively thin HMA layer on the surface. Usually it can be a 9.5 millimeter. You know, it doesn't have to be heavy, doesn't have to be intermediate. A small matrix or a nominal maximum size can be, you know, like a number 8. And then you can just mill the surface off and replace it every 8 to 10 years whenever you need it. You know, you're going to have less cracking and improved fatigue life because of the lower tensile stresses at the bottom of the asphalt, because it's not a structural layer. The unbound base carries the more loading than the conventional flexible pavement. And it's 6 to 8 inches is the optimal that we've found. And you look for, like I said, the minimum of 100% proctor on it. So let's talk about South Africa for a minute and some of their protocols there, which if I hadn't have really been exposed to some of their work, I probably wouldn't have pursued it as much. But when an entire country finds a pavement design that really works well for them, then to me it has to have some merit and validity. And why would we not want to embrace that concept and go learn about it and study it and see whether it has validity where we are? But are there a lot of people out there running out to discover about what this pavement structure is like? No. And why is that? That's a political question, and I won't go there right now. So, we see that some of their gradings, this is the VDOT design range in terms of what they put on their unbound aggregate basis. But we see they're very similar to what we have in the G1 range. These are a couple of important concepts, and I'm going to read them. It's important to note that for design purposes, the surfacing is not considered to add any structural value to the pavement. This is why the asphalt industry is not real keen on me. In the calculation of the life cycle cost of these pavements, particular attention should be paid to preventative surface maintenance. The other is, in South Africa, we typically do not assume that the HMA layer will provide any structural life to the pavement. We typically use relatively thin AC layers and would design the remainder of the structure to carry the loads. When the surfacing deteriorates, we mill it off and overlay it. We often overlay with seal or thin AC as part of the normal maintenance procedures. So I can't really show this slide to most of the asphalt community because they usually walk out. So let's talk about their design protocols. I found this was interesting. Pavements with high quality crushed stone are capable of accommodating traffic demands up to 50 million standard easels. The optimum thickness for the G1 base is basically 6 inches. If a pavement with a crushed stone base is maintained with resurfacings at appropriate intervals, the pavement can provide service for an indefinite time. It sounds like perpetual pavements, sort of. I think somebody else said that though. And the high quality, high density crushed stone placed in a thick cemented subbase showed the least permanent deformation under loading and was also the least sensitive to moisture. So, these sounds like some pretty compelling arguments. They've utilized mechanistic empirical design since the mid-70s, actually. You know, we're just starting to get there with our new MEPD design guide. And the transfer functions that relate to strain, stress, to field cracking are critical in understanding how this structure works. And different transfer functions are used when you have thinner asphalt layers. So the existing transfer functions that might be out there for flexible pavements aren't necessarily going to work for these inverted concepts. Okay? So we have to be careful because we're using an older system to predict something new. This is the South African version of your Atlas. Okay? So they drive this baby out there. They don't have to crawl out there. You know, apparently they can take it out to a road. What I like about this, I think, is that they can drive it to a road they've built. and then test the road in place. I think that'd be a great QA, QC control for the contractor, you know? So, let's look at this criteria here. This is their major interurban freeways, major rural roads, very important in terms of category. Service level, very high. Risk, they want very low risk. Traffic, equivalent traffic loading 3 to 100 million easels over 20 years. Pretty demanding structure. And here is their highest level: 2 inches of asphalt, 6 inches of unbound aggregate base, and 12 inches of CTA. That's their primo to 100 million easels. That's for dry areas, and then here's the wet regions. A little bit different, a little bit more cement treated base at the bottom. So, these are some of the things that we've discovered since. Louisiana discovered that they were having issues with reflective cracking. So what they did is they began to put what they call an interlayer in. Basically, it's an unbound layer in the midst, and that which seemed to stop the reflective cracking. So they tested this for like 10 years and discovered a 50% reduction in cracking versus their normal flexible pavements. They used an ALF to actually test several sections, and found that they carried over 4 times the normal load that an ALF would. So they adopted the stone interlayer base course as a design standard option on the projects, and they've completed 54 projects. This is in 2003, so there's probably more since then. So they found that this does work as far as using this interlayer concept. So let's talk about some of the test sections that have been built in the United States. In 2001, we built this Lafarge quarry entrance, and the Georgia DOT in 2009 built a section in LaGrange bypass. In 2011, Capstone built a section at their Bull Run plant in Northern Virginia. And in 2012, Bryce Simons built with the New Mexico DOT, built a section on Raton Pass, which is some of the highest that we have. And then in 2015, Vulcan Materials built a quarry road at their quarry in Pineville, North Carolina. So let's review some of these off the bat. So this is the Morgan County. It had 3 inches of asphalt concrete, surface mix, 6 inches of base, 8 inches of cement treated, and then they had 2 inches that they had to add to the unbound aggregate the soil profile in order to bring the CBR value up to get what they're looking for. So since 2001, we've had good rutting, good performance, no rutting, no cracking on the inverted section. Although the traditional section has encountered some cracking at the entrance where the trucks are coming in and out of the quarry, the normal pavement structure. So we can see that they used from 14 to 18 on the standard DOT method in Georgia in terms of how they compacted it. And then also the 10 to 14, they wanted to try the slushing technique, which Errol tells me you've seen one of the videos from South Africa about how that works. I think it's really kind of cool to do that, because if you've been out on and watched a paving or a job where you're actually compacting it, you can actually see the water bubbles and the fines come up from the structure. So, and the guy from South Africa did a talk at TRB a couple of years ago, and he said you can tell when it's really good. You can take a hammer out there after it's done and you hit it, and it'll ping like you're hitting a piece of steel. So he goes, then you know that you got it right. And he who's been building these roads for some time swears that the slushing technique provides that last little bit of interlock that gives you that ultimate strength that we're really looking for. But we haven't really tried it yet significantly in the United States, except for in this location. So this was the section that we built, and most of you have seen the video, so you kind of know what it is in terms of how it works. So you actually compact it first, and you get it pretty tight as far as your normal compaction. In the U.S., we'd probably quit then and move on. But there's one extra step is the slushing, where you then flood the surface and do high frequency, low amplitude passes with a vibratory roller, and that begins to vibrate all those fines up out of the structure. And then you remove all the superfines, and you end up with a real hard layer at the bottom. So since, as of 2009, which is a while ago, we've had 1.1 million easels. I would like to figure out how to update this, but I don't know anybody that's there any longer. So, and no shrink cracking was noticed. So we move on to LaGrange bypass now. This is the Georgia DOT, and it was built right in here. It's like 7/10 of a mile. It was on an originally intended concrete pavement. So this was the original PCC pavement here, 9.5 inches of Portland cement, 10 inches of grade aggregate base, and then the subgrade. So they built this inverted section with 1.5 inches, 3.5 inches of asphalt, 6 inches of unbound, and 10 inches of cement treated. And again, they did some blending of aggregate base to stabilize the subgrade. Placing this CTA. This is the finished project. This, I think, is the significant slide. So if you look at the cost analysis between it and you use the PCC, you can see the initial cost was more than the inverted, but if you take the inverted and you look at the 10-year maintenance, you're going to add additional, I guess I could use the pointer, couldn't I? Yeah, there we go. Resurface it at 10 years, at 20 years. So, and then the 30-year life cycle cost would be this relative to the rehabbing that you'd have to do at the 30-year cycle on the concrete. So you end up with a net savings they considered of about $140,000 on that section. So it has some merit. We were concerned about it when they first built it because it was turning into a truck. Actually, as the trucks were turning off of this layer. And we're concerned because of the thin asphalt that 3.5 inches of asphalt that we might have some skidding from the tire tracks pushing it and pushing it up. But so far, I'm not aware of that having happened on this particular section. So the one I'm most familiar with is the one that the Capstone built in Northern Virginia. This is the quarry here. Some of the students were asking me before, how long quarry might last. This particular quarry, we're expanding it out to here. We expect this quarry to last about 100 years. And when it's finished, at 400 feet deep, the bottom will be 15 acres, large. So you can see it's a very large infrastructure. And for Capstone, which is the company that owns this quarry at Bull Run. So you can see where we've cleared the pathway for the new bypass. Some of the things that I really wanted to do, because as a part of ICAR, we invested a lot of money in research in unbound aggregate base. And some of that was, I wanted the opportunity to use some of that knowledge. So for this one, we thought, well, we could do the design. If we could build it and have somebody instrument it, and then we could performance test it as time goes on, would be great. And actually, it turned out to be a good collaborative effort because Federal Highway came in, and they're actually the ones that instrumented it for us. And the DOT, Virginia DOT, was involved from a standpoint of being aware of what was going on and helping us troubleshoot some of the areas when we needed to. So this predictive aspects of ICAR is what we wanted to use. So when we designed the inverted base at Bull Run, we characterized the materials using the design equations that we developed in ICAR protocols. Reza Ashatini is the one that did the design on this for us. He's currently, let's see, I got to get this right. There's a difference between associate and assistant. I think he's an associate professor now at the University of Texas, El Paso. So he's still connected and still involved, but also I think the current MEPDG, as I understand it, still looks at pavement design from an isotropic point of view. It's vertical stresses, and because a lot of the work that Errol has done over the years, we know that that's not necessarily the case, and it's really an anisotropic environment because we do have horizontal stresses as well. So, especially with the moving wheel loads, which Errol's the first guy I heard that about from, and that was probably 15 years ago. I thought that makes sense. We're looking at a dynamic system, not a static system. So I felt like we had improved upon the entire knowledge base of what was really going on. And now you have these atlas out here actually testing that premise on many of the pavement sections that you're building. So I wanted to compare it to the MEPDG and using the ICAR protocols regarding what we'd learned from ICAR. So, and then compare the construction costs and alternative designs. So that's kind of where there was the little strip there in the middle of the woods, and that's what it looks like after we cleared all the woods out of the way. So this is the pavement at the original section, the inverted. Now you see that we have like 5 inches of asphalt on this, which is a little bit more than we wanted. We were really just hoping to put like 2 inches on it, but none of us were brave enough to go that distance. I think that we'd like to have some more sections and try less asphalt. But that's what we came up with, because we're using some old models to predict fatigue life, and we're using old models, asphalt models, to predict rutting. And those models may not be appropriate to this design protocol, so we kind of mixed two different worlds together. But this, you can see this standard design, and then the cement treated, unbound, and the 5 inches of AC. So it was a great experimental section. We picked is level, it was straight, no curves, and it was all in cut. So what we have below us, as a matter of fact, the FWD work that we did there, it was really difficult to interpret it because there was just rock below us. 6 inches below the bottom was rock. So it was difficult to understand what was really going on with some of the FWD work. So we had a 400-foot section of inverted design, and then we buried, Federal Highway buried the instruments in the test section here. And this was the inverted design, and then we had the control section with the existing pavement design and the instrumentation location. So we buried the same instruments in both spots. And in the middle, we had a traffic monitoring system. So we still are operating that traffic monitoring system today. Although the sensors in the road, the embedded sensors, are starting to wear, and we're going to have to make a decision whether we're going to revamp it or whether we're going to just drop it. I would like to keep it going for at least 10 years, so we have 10 years worth of data. Also, because this is not a private road, this is the DOT owns this road. So we had to take an existing road and condemn it so we could own it, and then give them all this land and pave it all for them and build the whole thing on their behalf because it's a public road. So because we're trying an innovative design, we had to warranty this. So the company had to warranty this design, said if it fails within 10 years, then we have to go back and replace it or put in what the original design was. So those are some of the issues that we had to deal with at the time. Fortunately, I didn't get a bunch of lawyers involved with it, so it was pretty simple. So that's kind of what we did, and some of the we used this, and then we used the ICAR protocols, which I think were really important. And I think what's really critical is this data here. If you use the linear isotropic, you discover that you have the existing models. You discover that you have tension in the base layers, and so how can you have tension there? Whereas using the anisotropic, look, we still have some small amounts of compression, which is what we would normally expect to see. This is what you pavement design engineers tell me, because this is relatively foreign to me as a good old mining engineer. So then we did the traffic calculations to determine how many easels does this thing need to survive. We wanted to go 30 years, 17 million easels is what the design is. This is all Reza's work. And then he did like 70 iterations of linear programming. And we finally, the only one that came out green, because remember, we're using these fatigue models and rutting models that are asphalt related. Whether they're applicable to this design protocol, I would question that, right? So anyway, this is, we had nothing better. So it's just, okay, when we hit the green lines, that said, okay, we're past 17 million on both rutting, it should last that long, and we needed to have this design, which was 5 inches of aggregate. 5 inches of pavement, asphalt, and then 6 inches of unbound aggregate, 10 inches of CTA on a 10,000 PSI subgrade. So those are the design protocols using the models that we developed. The nice thing was that we instrumented, and I just told you, 2 different ways for both the pavement instrumentation and in the traffic. So I wish Ahmad would have been here when we put all these in, because he probably would have made sure that they were done right. But we put them in anyway. So the Federal Highway, I really do appreciate their work in this area. It was a godsend for me and the company, because they invested a lot of time and energy, and it's something that we know nothing about from the private sector point of view. So we installed all the equipment, the strain gauges, the traffic, and at the end of the day, what was the cost? So if you add all this up, these are all the calculations of all the costs for everything per 100 foot. The original section would be $21,000 per 100 foot. The inverted section was $16,000 per 100 foot. So basically you end up with like a 22% savings going from the design protocol that was there to the inverted. These are some construction slides. We had to drill and blast, right? So drilling, blasting. And then we had to dig it all out to get down to the grade. So this is a straight section. It was all uncut. So it was all very consistent. Notice some of the nice sized chunks of rocks that came out of there to rip it up. This is the section where the inverted is. You can see that the 2 zones there where we buried the instruments. We actually had a time-lapse camera right there, and so we kind of did a time-lapse for a lot of it. And this is the finished product. You can see the traffic solar panel there, and then this blue box is what hooked into the instrumentation and the pavement itself. What was cool is because we were building this, we had a demonstration project and invited everybody to come and participate. We had a pretty good attendance when we had the presentation, and you might recognize some of the participants who actually did talks that day. This Mr. Tootmuller, and then Douglas Cortez did his PhD on inverted at the Georgia Tech with Dr. Cardoza, and Nelson Gibson, who's was with the Federal Highway, who did all the instrumentation on our behalf. And then Reza is the one that did all the design work. And then Shane Buchanan was with Vulcan at the time and has been involved in inverted quite a bit, but he moved over to Oldcastle now, so he may not be as involved in inverted as he once was when he was with the Agger guys. So this is important here, I think, just so you begin to get a grip. So if we look at the solid particle density, if you had a solid mass of rock at 2.9 specific gravity, you're going to get 181.7 pounds per cubic foot. That's 100% density, right? So if you look at 86% density of that, which is what the South Africans attempt to get, is 156.2 pounds per cubic foot. This material is called dye-based, so it's one of the best construction stones for pavements probably in existence. It's very homogeneous, very consistent in terms of what it is. So the modified Proctor that we got, the T180, was 151 pounds per cubic foot. So the northbound lane, these are some of the densities that we actually achieved. We got 161.7 pounds per cubic foot, or 88.9% of the maximum density, or 106 of T180. Now, who would have thunk it that you could get that kind of densities in construction? The center lane, not as good, but still pretty good. And then the southbound lane. So, for the most part, you know, and at least in those three locations, we did achieve getting those high densities that we know is critical to the success of this design. We did not slush it, though. I wanted to take 100 foot and try it, but we just didn't. So these are some of the activities that we, you can see the LV going in. It was nice at the demonstration because we had all the instrumentation out so people could see it. We had it kind of profiled so you could see where it was actually going in the pavement structure. So it was kind of cool in that respect. So these again, just to recover. Virginia. Let's talk about New Mexico. I don't have a lot of data on New Mexico except the design. It was in Raton Pass, Interstate 25, 1.5 miles. They get 54 inches of snow per year. We thought this would be a great test to see how well it performs. And it was built in 2012. Using 3 inches of HMA, 8 inches of aggregate base, and 10 inches cement treated. Bryce Simons is the one that was responsible really for getting this through the New Mexico Department of Transportation. He's since retired. And he did come back to do an inverted section that we had at TRB a couple of years ago. But I don't know how this is performing, but I haven't heard anything bad about it yet. Do you know anything, Earl? Have you heard anything about this section?
Not really. That's
Okay.
what I'd like to follow up, actually.
Okay. Now this is the new one that built recently. This one you might not have heard about too much. I know Kevin hasn't been. If Kevin came, this is probably what he'd talk about. Vulcan needed to relocate a road near their quarry in Charlotte, North Carolina. Except I hid my watch so I can't see how much time I'm using. Okay. So they had, it's nice because they built a control section and an inverted section on this new road they were putting in. And they also had a pug mill capable of cement treated aggregate. Not all aggregate producers had this capacity at each quarry. So that was all good that aligned. This is the picture of the quarry. They're really interested in expanding their reserves, and they needed to basically open this area up so they could expand their reserves and start mining this. And this road was kind of in the way, so they had to move the road to a new alignment. And so half of this is inverted, this section, and then the northern section is a control. So they're estimating 1.5 to 2 million easels over that 20-year span. And they used the South African protocol as a concept to design around. So they ended up with 1 inch. These are North Carolina standard mixes. with the intermediate of 1.5 inches. So we had a total of 2.5 inches of asphalt, 6 inches of aggregate base, and then 8 inches of cement treated. And they were trying to achieve the 8 inches, 97% modified. They're trying to get at least that dense when they put it in. They weren't doing anything special. This is the standard ABC aggregate base course for North Carolina and standard grading, with only 2% cement. And they were looking for a compressive strength of 550 psi at 7 days. This is design. Marshall's like scrunching his face back there.
2% won't get you 550, will it?
It depends on the quarry.
Oh,
Yeah, it does. This Pineville quarry is an igneous, pretty tough stone there. And basically you can see the grading over there in terms of the grading of the base that they used. So they achieved a density of 99.2 on the cement treated, which was okay for, you know, I mean, it's cement treated base. And then they sprayed it to tack it so they could cure for 7 days. But Kevin says that he couldn't control the cement sometimes, and it would go a little crazy. Sometimes we have a little trouble with that. And usually they figure if they kind of, you know, anyway, we got a little bit higher than 2%, he said, on average. So our average final strengths were 1,500 psi, which is pretty up there. And it'll be interesting to see if we crack it. So that actually you can see where they cured it and let it sit for 7 days. So this was the Proctor was 153 pounds. They're looking for 102%. Their target was this. Their specific gravity, this material is pretty high as well. And they were trying to get 85% of the apparent specific gravity. These are some construction photos. This is the subgrade. Clay, subgrade. Putting down the unbound aggregate base on top of the cement treated. Slushing. They didn't slush it, they just, North Carolina kind of does, they get it really wet. They put it down kind of dry, and then they run water trucks over it and get it pretty wet, and then they compact it. And they did it on both sections at the same time, and the roller driver who was doing the compaction work said that when he did the unbound aggregate that it would bounce. He could tell that it was different because it was bouncing a lot more. So they got the 99 on the conventional pavement, and what he was looking for 102, he got 103 on the inverted section on the unbound aggregate base. So he achieved that as well. And they didn't change the methodology, and this is where the operator reported that he could tell there was a difference because it was bouncing. So he had something, a platform to really compact against. And their normal DOT mix. So it achieved better density on all layers on the inverted pavement than they expected, and the importance of a good foundation. So this is the conventional that they used, and the unbound, the inverted. This was $35 a square foot, $40 a square foot, 11% less in cost. What's cool about this is now they've gone in with the FWD 5 different times over the time it was built, September 2015 to April 2018, and done FWD work along the entire length of the road. And then we're going to look at those results. So this is the inverted section, and this is the standard section. You see any difference? So the deflection was about 15 mils on the standard section and 7.5 on the inverted section in terms of deflection. So we can see that something might be going on here. You know, there might be some benefit, and obviously the key to the inverted, again, is the unbound layer being stressed to the max. Maximum hyper density. And I think if we slush these sections, we'd probably even get a denser structure that would be able to sustain the level of traffic South Africa has for those many years. So, it's relatively easy to construct. No new or high level techniques. It's standard techniques that people are used to. It's stiffer, and it's 11% less costly for them when they built this section. So you're getting a stronger pavement at a lower cost. So what's the future? Well, Tennessee, we're looking and working at a 1.7 mile section of inverted. We submitted a pool fund study a couple of years ago and circulated among all the states, but we didn't get too many takers. I think they were asking, at least what I've heard back, is they were asking for too much money over too long a period. And as a result, we haven't found a DOT to kind of help us rewrite it and send it out again as a different, so we've been trying different pathways to get a little bit more interest on a national level. TRB Aggregate Committee actually submitted a synthesis proposal to NCHRP, but we need to revamp it and resubmit it because we didn't really get any support going in that particular direction. And Errol and I were talking about this last night to help educate me about the proper process to move it through. And then also the North Carolina Department of Transportation is looking for a section where they, in their pavement work building, to build a section on as well. So those are the options that we might have for the future. And with that, I'm done. And on time too, how about that?
Excellent.
So,
I think we can have several questions for you.
please, don't ask me any technical questions, okay?
Randy,
Yes?
you probably remember Frank Nichols.
Yes.
Okay.
Oh, with National Crushed Stone Association.
And his former Virginia DOT. When he was at the DOT, he built a lot of sections with cement stabilized subgrades, ag bases, etc. And that, I think, was sort of the beginning of the interest in, this type of design.
Okay.
Yeah. And he was really hard for it on that. And then when he got to the Stone Association, he still was pushing that.
Yeah.
The other comment I have is, if you use cement treated ag base from your local quarry, that's one thing. The other option that some folks probably go for is doing in-place stabilization of the current subgrade, maybe to a little thicker section if need be. But if you don't, have to haul that material around, while you can do in-place stabilization and get. We currently at IDOT, if we have design a conventional flexible pavement, if it's over 8 inches in thickness for the base, we permit the use of a stabilized or modified subgrade. We call it stabilized subgrade beneath that. And I'm not sure how many folks are using that.
Do you use hydrated lime or cement stabilized for the subgrade?
Which cement mostly, yeah.
Okay. Yeah, that's certainly an option, I think. I'm going to take a quarry position for a second as an aggregate producer. And for every 100 tons of material the aggregate producers haul from the pit face to the crushers, 30 to 50 tons of it ends up being base. The rest of it becomes clean stuff. So from a sustainability point of view, the aggregate community is, and if there's not a lot of construction, where you can utilize that base, you begin to pile it up.
Yeah.
And we've seen that the base piles grow to such an extensive state that some companies now are actually taking the base, running it through a special plant, and taking it apart, and recovering all the stone and making 57s and 8s out of it. So, and then we end up with all these, again, quarry fines, minus quarter-inch material, that now we're looking for a home for that stuff, okay? And we find you might be able to get rid of part of it, but now the asphalt community, at least in Virginia, is saying, we want, because of all the wrap we want to put in our mixes now, we don't want dust that has 9 or 10% minus 200. We don't want dust that even has 4 or 5% minus 200, because we can't put as much wrap in it because of the fines that are in the wrap. So we want you to give us washed screenings, minus quarter-inch that's been washed, at 2% minus 200. Well, most of those screenings are going to be at 13 to 14% minus 200. So in order to get it, where is all that minus 200 going? To get it from 14% to 2%. Guess what? It's going into huge, massive ponds. Okay? Now, what are we going to do now with all that stuff? Somebody asked me what we're going to do, you know, what do we use our quarries for? We're finished with them. We might be filling them up with all this minus 200 that we have no home for anymore. So then we have to be creative. You know, necessity is the mother of invention. So we can begin to look for options and opportunities to take advantage of that minus 200 and utilize it for a beneficial product in some other market, some other place. Maybe it'll make great baseball field surfaces. Who knows? So,
Well,
yes.
you downloaded the report, our recent report actually, some worked on that with me.
Yes.
I'm not sure if you had a chance to look outside.
I did.
You did, okay.
We went outside, but I didn't go to the Quonset hut. Is that, I'm not sure which.
You saw the stabilized QB sub-bases and bases?
No, I didn't. I just went and looked at the atlas.
I gotta show you that before you run to the airport.
Okay.
Any other questions, comments?
Yes.
So, you know, referring to it as an inverted pavement, and I guess, are we talking about the difference between the overlying HMA and then this very highly densified aggregate? Because to put that aggregate on top of a cement modified base, let's say, really if you're looking at the performance, how do you expect it to work, then that's not inverted. You know, you're getting something that has a very much higher level of performance out of this.
Yeah, it depends on what you mean by inverted. So, you know, inverted from a strength point of view, or inverted from a, when we say inverted,
Nominally, right?
it's like relative to what we're doing today.
Sure.
From a standpoint of, you know, typically the weakest layer is at the
Mhm.
bottom, so the perception is that the unbound aggregate layer is weak. You know, it's assigned a structural value of what, 0.14. So obviously everybody knows, we've been raising pavement engineers for the last 50 years, and they all know that base is the weakest part because it's 0.14. But we need to change the paradigm and think about it as a different product, especially if we stress it. If it works well under stress, then by golly, let's stress it all that we can and make it work for us. We just haven't done that, I don't think.
So your comment made me think something else. Has there been anything to look at what an equivalent, say, structural number would be for this very dense, unbound aggregate?
No. And frankly, we know that the current MPDG, the AASHTO ware, is faulted. At least that's what the current PI that's doing 105 is saying. Why can't Dr. Little in Texas A&M right now? That work is supposed to be completed by the end of it's been last year, June, then it's January. You know, we're like 18 months late on that report. But ideally, the MPDG did not properly assess the structural value of the unbound layer because that was primarily either an asphalt program or a concrete rigid pavement program. So it didn't really properly modify or properly address the structure of using it from a compressed, densified layer and the value of that. At least that's, in my world, that's what it looks like.
Brad, is anybody doing any work on the shear strength of these really super high density granular bases?
The only one I know is doing with shear work was some of the work that Errol did out of
Can you get
North
to
Carolina.
105% modified?
Yeah, right, you can. You have to beat it.
Are you getting there?
We didn't try that in a specimen.
Well, yeah,
Something to try.
You know, to do it the right way, like Earl and I do it with lily paper or GT paper, whatever, you need shear strength as
Yes.
well as margin. And I would imagine the shear strength of this stuff is really, really out on the high side. You know, Gray, remember old Joe Gray at NCSA did all that work on shear strength and density. It shows up
Yeah.
all the time. Yeah, so that'd be an interesting thing to try it out to some interesting young researcher or something.
That's a good idea.
Yeah. Yes.
So Marshall's comment made me think of something also, talking about the difference between, they're looking at the percent of solid density versus modified Proctor. And I thought what struck me is that maybe that is absolutely necessary to look at it as percent of solid density, because when you slush it, you're eliminating fines and you're actually changing the material. It's not the same material you would run a Proctor on. So, you know, I know that's one of the things. If you're field density testing, you have to make sure what you're testing is what you ran a Proctor on. And if you're removing fines, it's a different material.
Yeah, that's true. That's a good point.
And then I was just curious, you know, since slushing removes these fines, and it probably is a necessary step to have them there, densify it, wet it, and slush it, but has there been anything where they've looked at a different gradation that says it's deficient in the fines to the point of your finished product? And is there a way to just compact it without having initially had those excess fines? I mean, it may not work.
Typically, it's gonna be very difficult to get an unbound aggregate base that's produced out of a quarry to not have at least, I mean, if you work at it really, the only way we could reduce the fines is add more stone.
Sure.
So if we had like 15% minus 200, we'd have to put more 1-inch stone in it, or 3/4 inch stone. Of course, in base, the stone might be worth $5 a ton. But as clean stone, to put in asphalt or concrete, then it's worth $15 a ton. What would you want to do? That's one of the downsides, I think, of this concept, is the perception in the marketplace could be that aggregate people support this because they're selling a lot more aggregate base. So that should be good for them. Well, the problem with us is that it's not necessarily, because we have a much better margin on the stone we sell to the asphalt people and the concrete people than we do the margins on our base. But we think about it as more greener and more sustainable because it fits better with the production that we have of base in a natural quarry. It's more a sustainable mix. And where we're building roads, it worked out. But the interstate system is virtually ended, you know, and we're not building a lot of roads any longer, so we have an excess amount of base.
Yeah, you need the fines to be able to compact, but then slushing, you don't need that for the use
Right.
period of the road.
Right.
You get those
Yeah.
out.
The only place I've seen slushing, and I have observed what it is, but by accident. You know, they put it down and you get a lot of heavy truck traffic over it, and you see that,
Yes.
that mush on top, and you get a very solid aggregate base underneath that.
Yep. Yes, sir.
Okay, quick question. Randy, now in Virginia, I mean, don't you sell some of the fines for to the agriculture people? Do you do that?
Only if it's limestone.
Limestone, yes. And
Now, in the Shenandoah Valley is limestone.
yeah,
The Piedmont is all metamorphic.
yes.
So from like I-95 to the Blue Ridge is all metamorphic.
So you do sell the limestone fines?
Yes.
Yes.
To-
Okay.
When I was with Luck, they had a couple of limestone quarries, and we did sell a lot of lime and use the fines.
Okay. My
And lime?
other question is,
egg line base.
Yeah. My other question is, I know that the converted pavements has been used extensively maybe in South Africa and Australia. What's the experience so far, or what's the longest experience we have in the United States? Which state has been doing this more than others?
The only sections that we have in the United States is the Morgan Quarry inverted pavement built in 2001 on a quarter-mile section of road.
But I thought that the Louisiana are doing some, isn't it?
Well, they call it an interlayer, but it's that, they're putting an interlayer of unbound aggregate in there. I don't know how consistent they are, but I do know that they've found it being successful. I don't know if that's a standard design protocol of them or not. Also, I know that RACA has found a couple of counties in Texas are utilizing an inverted concept above a stabilized subgrade.
I see. So if I can ask you, is there any state now using this?
I'm not
So
aware.
it's going to be just trial and error at this point?
I'm not aware of any state that
Yeah.
in their bag, their tool of design protocols has any inverted design protocol in there. And there's nothing in the MUPDG, AASHTO, where about it. And there's no protocol for it, so it's, it's virtually non-existent, especially if all the states are gonna go to AASHTO eventually.
Yeah, I would think Louisiana has the best experience. They call it a different name.
Right.
They give it a different name, but I think
What is
that's.
the name they call it?
They could just call it an interlayer.
Interlayer.
Yeah.
It's interesting. Yeah, because I thought that they are doing something. That's why I asked you.
I'm talking too much for an old retired
Go
pro.
ahead.
Anyway, the epitome of a dense graded aggregate base is a rubbleized concrete layer. We've got a section of I-57 down by Effingham, and it's got a 6-inch, it's rubbleized concrete over a garbage sub-base, old concrete base, old CRCP, with a 6-inch hot mix asphalt overlay on top rubble. At one time, the last time I saw the numbers, we had 16 million pieces on that section, clean as a hound's tooth. Bill Butler and I looked at it a few years ago. It's clean, nothing's
Still
going
good,
wrong.
huh?
No fatigue, no, rutting is minimal, but that's about as dense as you're ever gonna get. Concrete, and then you just fracture it up.
Just fracture it up,
And you got-
cracking.
Oh, tremendous airlock. So it's tough to model the damn thing, but it's a super base. It's-
I would think it would be, yeah. 'Cause
Sounds great. All right, let's
Yeah.
give a big round of applause.